Hey guys, in this video we're going to go through the probability practice test. The first set of questions is about simple probability or probability of a single event. In this case, we're taking a bag of Starbursts and picking one of those Starbursts out of the bag. Okay, the Starburst color are pink, red, orange, and yellow. So we're going to assume that there's one of each there, which means we have a total of 4 Starbursts. We want to calculate different probabilities of different outcomes happening, and whenever we calculate a probability, we're going to take what we want to happen out of the total. And by that, I mean we're going to set up a fraction where the numerator is the total number of favorable outcomes. How can we get a desired result? And the denominator is the total number of outcomes. So since we have 4 Starbursts, my denominator is going to be 4 to represent the 4 possible outcomes. Now in the first one, it says, what's the probability of drawing a red Starburst out of the bag? Since only one of the Starbursts is red, my probability is going to be 1 in 4, or 1/4. You can leave your probabilities as a fraction, or you can convert them to decimals or percents. If you leave them as a fraction, you want to make sure that they are as simplified as possible. So if I were to leave it as a fraction, 1/4 is simplified, can't be simplified further, so I would leave it like that. To calculate the decimal version in your calculator, you would take 1 divided by 4. You would find that it's 0.25. As a percentage, you would move that decimal 2 places over to the right, and you would find 25%. Okay? Unless the question specifies how to leave your answer, you can choose if you like fractions, decimals, or percents. The second question here asks for us to calculate the probability of drawing a pink or a red Starburst out of the bag. So I'm going to think of the possible ways that that could happen. Well, either I pick the pink or the red, which means we have 2 favorable outcomes out of the 4 possible outcomes. So we have 2/4 as our probability. That simplifies down to 1/2. As a decimal, that would be 0.5. As a percentage, that would be 50%. Next up, we have the probability of not drawing yellow. So that means we're talking about the other 3 possible outcomes, pink, red, or orange. So our probability is going to be 3 out of 4, or 3/4. That's simplified. As a decimal, that would be 0.75. As a percentage, that would be 75%. Again, unless the question specifies how to leave your answer, you can choose which version of the answer you would like to leave. Next up, we have a simple probability, but it's changed slightly. We're going to think about the difference between theoretical and experimental probability. Okay? So in this scenario, a student has flipped a coin 20 times, and out of the 20 times, it has landed on heads 15 times and tails 5 times. Okay? We want to know what's the theoretical probability of getting a tails on the next flip versus the experimental probability. The theoretical probability is what we expect to happen. Okay? So ignoring the experiment itself and thinking about a coin. Well, a coin has 2 sides, so that's the total number of outcomes. And if I want tails, there's only one way that that could happen. One of the 2 sides is tails, which means the theoretical probability of the getting tails on the next flip would be 1/2 or 50% or 0.5, depending on how you want to leave your answer. Compared to the experimental probability, the theoretical probability is the theory of what you expect to happen, what should happen, where the experimental probability is based off of the experiment. So this is based off of the trials that were conducted. Okay, so now we're going off of the data here of what happened in those 20 flips. Okay, so based off of those 20 flips, only 5 of them were tails. So in the next flip, using that as the probability, out of the 20 flips, 5 of them were tails gives me the probability of 5 over 20. 5 desirable outcomes out of the 20 outcomes we ran through in that experiment. That simplifies down to 1/4. If you leave it as a fraction, 1/4 would be the best way to represent that probability. Next up, we have another topic from the first lesson, which is called the fundamental counting principle. Now, this is a way to calculate the total number of combinations when you're making multiple choices. For example, when you're picking something to eat, if you have multiple choices like an entree and a side and a dessert, there are many different combinations of meals that you can take. So here we have a new restaurant offering a limited menu. Guests can pick out an entree, a side, and a dessert. The choices are listed below. So underneath entree, I see 4 different choices. Underneath the side, I see 3 different choices, and dessert has 2 different choices. If I want to know how many combinations I can create in my order, I'm going to look at those number of options in each choice and multiply them together. Okay, this assumes I'm only picking one item from each category. Right, so I think of these each as choices: entree, side, and dessert. I have 4 options for the entree, 3 options for the side, and 2 options for my dessert. I can calculate the total combinations by multiplying those together. 3 times 4 times 2 gives me a total of 24 different combinations. Now I can limit the number of combinations by reducing the number of options that I have, or reducing the number of choices that I make. For example, if you have decided that you are getting ice cream for the dessert, you now only have 1 option for the dessert. You're eliminating the cake option, so that means there's only 1 choice to make, which you've already made. Okay. Assuming we haven't picked out the other 2, we're going to keep our options here as 4 and 3. To find the new number of combinations, I'm going to multiply 4 times 3 times 1, which brings that down to 12. 12 different combinations or ways that we can order this meal. Next up is geometric probability. Geometric probability is going to start out similar to our simple probability, and that we're going to think about what we want to happen over what could happen, our total number of outcomes. But instead of choices and thinking of options and outcomes, we're going to deal with area. So here we're calculating the geometric probability that an object dropped in these shapes will land in the shaded area. So what we want to happen is it to land in the shaded area. So our numerator is going to be the area for the shaded regions. Our denominator is going to be the total area, looking at where could this object land. Taking a look at the first one, I notice my shapes here are rectangles and squares. Okay, so calculating the area of rectangles and squares is going to be base times height. So for my shaded area, I'm going to take base times height here is 5 times 2 and find that that has an area of 10. That's going to be the numerator of my geometric probability. My denominator is going to be the total area. In this case, our total area is going to be this biggest shape, which happens to be a square. Okay, the base is going to be 5, and the height is this total length, which I have to take the 2 plus 3 to get a height of 5. Okay, so that area is going to be base times height, 5 times 5, which gives me an area of 25. Okay, so again, that was the area of the square, which is the total area, and that first area I calculated was just the area of the shaded region. Okay. So putting that into a probability format, 10 over 25 would be the probability of an object landing in the shaded area. If I leave my answer in fraction form, I want to simplify, so that would be 2/5. Okay. You can also convert it to a decimal or a percent. If you convert it to a decimal here, it'd be 0.4. As a percent, that would be 40%. In the second example, calculating the shaded area is going to be a little bit more complicated because the shaded area isn't a shape that I recognize. The shaded area is this rectangle with these circles cut out from the middle. So to find the shaded area, I'm going to need to take the area of the rectangle minus the area of each circle. Now the area of my rectangle is going to be base times height, and the area of these circles is going to be pi times radius squared. okay? And I gotta make sure that I take out both of them. So starting with the rectangle, base times height is gonna be 4 times 3. Kind of erase that, so I'm gonna double check. Yep, 3. Okay. The radius of my circle, I gotta be careful here. The length of this rectangle is 4, so that means the diameter of each circle is gonna be 2, which means the radius of each circle is gonna be 1. So I'm gonna have 12 minus pi minus pi, since 1 squared is 1. For this next step, I would need a calculator to take 12 minus pi minus another pi, and I'm gonna get 5.72, okay? And that's gonna be the shaded area again. Now the total area, I've kind of already calculated. This total area is the area of that rectangle, that biggest shape, which we said was base times height. Our base is 4, our height is 3, which means that total area is 12. So for the second probability, we're going to take 5.72 for our numerator, the shaded area, over 12. Okay, if I were leaving my answer as a fraction, this is where I would stop. If I'm converting it to a decimal, I'm going to type 5.72 divided by 12 into my calculator. Rounded to 2 decimal places, that's 0.48, which is 48%. Moving on to the second half of this unit, our next topic was contingency tables. A contingency table is a way to represent data that's been split up into categories. For example, if you ask people a question, you could categorize them based off of their answers to that question. So here we have 115 students were surveyed about their favorite snack and their favorite game to play. Okay, we can see the options for the snack across the top. We had 3 different categories: pizza rolls, chips and dip, and cookies. And then our options for the game are across the side, and there were 4 different options: Candyland, Monopoly, Wii Bowling, and Mario Kart. Okay. When we look at this contingency table, the numbers represent how many people answered that specific category, okay, or that specific combinations of categories. Along the edges, we have the totals, and we see that overall total in the bottom right-hand corner. That reminds us that 115 students were surveyed. So we can use this contingency table to pick out some numbers, how many people responded in a certain way, or we can use it to answer probability questions, like what's the probability that a randomly chosen person prefers pizza rolls? Okay, setting up our fraction again, what we want is them to choose pizza rolls, and our total is how many people were surveyed. So we're out of the 115 total. I'm going to look for pizza rolls, and I want everybody that answered pizza rolls as their favorite snack. So I'm going to go down to the bottom to find the total of that column, which is 44. Okay, so my answer here would be 44 over 115. Okay, and you can leave your answer in fraction form. Next up, it says, what's the probability that a randomly chosen person prefers cookies and Wii Bowling? So now it's not just cookies, but when I look in that cookies category, I want the people within the cookies category that picked Wii Bowling. And I find that that's 7 people. Okay. So my probability here is the 7 people that picked both cookies and Wii Bowling out of the total 115. This is our regular simple probability, but we can also ask some conditional probabilities. Conditional probability questions have a specific characteristic given to us. We're operating under the condition that some result has already happened. Like in this third case, it says, given that a person likes chips and dip, our total is not now everybody, but our total is the number of people who picked chips and dip. So if I look at the chips and dip category, there are 41 people that responded chips and dip. So we're out of the 41 people within that category. We want to know what's the probability that somebody from this group liked Mario Kart. So 41 is going to be my denominator, And when I look within that chips and dip category, my numerator is going to be the people within that group that liked Mario Kart, which is the 7 people in this box. Be careful with these contingency tables to read carefully. Take your time, double check your numbers as you pull them from the table. Lastly, we have Venn diagrams, and in this section you could be asked to use an already created Venn diagram to answer some questions about probability, or you could be asked to create your own Venn diagram based off of information given to you. So in the first case, number 6 here, we have a Venn diagram that's already created for us, and it's based off of this question: do you like pancakes, waffles, or both? Okay, and the probabilities were calculated and plugged into this Venn diagram. So in the Venn diagram, we can see the 2 circles representing the 2 possible answers, but we have to recognize that somebody could have said they just like waffles, they just like pancakes, they like both waffles and pancakes, or they like neither. Okay, so within this waffle circle, which I'm outlining in purple here, we have the 2 sub-responses. The 0.35 represents only waffles, but not pancakes. The 0.40 in the middle, that also is overlapping with pancakes, represents the percentage or probability that somebody said they like both pancakes and waffles. Similarly, underneath this pancakes circle, we have the 2 subgroups. Again, that 0.40 represents the people who said they like both pancakes and waffles. The 0.15 is the percentage or probability that somebody said they only like pancakes but not waffles. Okay, it's important to note that there's another number. This 4th number on the outside edge represents the people who said neither. We want to be able to have this other category for people who don't fall into either of the 2 options that we proposed. Now that we've kind of analyzed the different parts of this Venn diagram, let's go ahead and calculate some probabilities. So this question is phrased with shorthanded notation, probability notation. Instead of a full question, a full sentence, we have P for probability, and what we're analyzing in parentheses, so the name of the event or short description. So in this first question, we have what's the probability that somebody likes waffles? Well, we're not clarifying whether it's just waffles or waffles and pancakes, so that means we want to include everything in the waffle circle. So I want both components here, the 0.35 and the 0.4. So if I add those together, I get 0.75 or 75%. So that means 75% chance that somebody likes waffles. The second question here now says only pancakes. So that implies we don't want to include waffles. So we're looking underneath the pancake category, but we're not including the overlap. We want this 0.15, which is the people or the probability that a person picked just pancakes but not waffles. So just that outer edge of the pancake circle, 0.15. The next 2 use a special type of notation called the intersection and the union. This upside down U represents the intersection. That's the crossover where these 2 groups collide or intersect. That's referring to the both section. Okay, so I'm looking for this overlap, which gives us the probability of 0.4. The union is this symbol on the last question, which is the U, and the union brings everybody together. That's waffles or pancakes. Okay? We can think of the intersection as the word and, waffles and pancakes. We can think of the union as the word or, waffles or pancakes or both. We don't care. We want to collect the entire probability that somebody said one of the 2 categories. So to find the union, we're going to add up all of these probabilities within the circles. So we're going to take 0.35 plus 0.4 plus 0.15 and find that that total is 0.9 or 90%. The very last question asks us to create our own Venn diagram. And again, we're going to have to be careful with the wording of the information given to us. It says that 85 people were surveyed about if they have a pet dog or a pet cat. Now, we know it's possible for people to have both, and it's also possible for people to have neither a pet cat nor a pet dog. So we want to keep those possibilities in mind as people answered. It says 37 people said that they have a cat. We don't have any information about whether or not they had a dog. So that means we're talking about this entire circle. That includes the people that have both a cat and a dog, the people that have just a cat. It should add up to 37. I'm not going to fill in any information because I don't know how that 37 is broken down yet. The next statement says that 23 people said they have a dog. That's referring to the dog circle here, the second one. But again, I don't know how many of those 23 have both a cat and a dog, how many of them have just a dog, so I'm going to refrain from filling in the specific subcategories within the dog circle. That is until I read this next statement that says 11 people said they had both. Well, I know the both category is in the middle, so I can for sure put 11 there. Once I have this 11, I can go back to the other parts of these circles and fill in the information. Okay, the people that only had a cat. Well, I know that 37 people have a cat. If 11 of them also have a dog, I can find how many only have a cat by taking the total 37 minus 11, which gives me 26. Similarly, for the dog, I know that 23 people have a dog, 11 of them also have a cat, so the people who only have a dog must be the difference. 23 minus 11, which gives me 12. The part that people are going to forget is the neither category. Okay. It is possible for there to be some people who answered neither. Keeping in mind that we had 85 people total, let's see how many people are missing from this survey. Right now we have 26, 11, and 12 people represented underneath those three categories. Let's add those together and see how many people currently are represented in our survey. 26 plus 11 is 37, plus another 12 is 49. Now, if I want 85 people to be represented, I need to figure out how many I'm missing. So I'm going to take the total, 85, minus the 49 people currently represented in this Venn diagram, and find the difference. We have 36 people missing, which means 36 people must have answered they own neither a cat nor a dog.